We went over some important details at the very end of that video, and I know as interesting as I can be and as interesting as VPNs can go, at the end of a 15-minute video you might be fading a little bit. So let's go over these details one more time. As far as configuring the site-to-site VPN, I want to clarify something I said at the end of the last video as well. It's a 5-step process overall. We have the initialization of the entire process via what we call interesting traffic. We'll mention that again here in about 1 minute. Then we have IKE Phase 1, which is the IKE SA negotiation. Then we have IKE Phase 2, which is the IPSec SA negotiation. Finally, after all of that, huzzah, we have data transfer. And once we're done with our data transfer, of course, there's no reason to have the overhead of the upkeep of this tunnel of the VPN, so we want it to be torn down. That's tunnel termination. Now, IPSec is not going to just start working by itself, and when you configure IPSec, it's not just going to start protecting every packet via IPSec. And we don't really want that. That's a lot of overhead. We're going to pick and choose what traffic we want to be protected this way. And we're going to use a crypto access list. And again, I want to mention, don't get intimidated by this name because it sounds like something really mysterious. Ooh, crypto access list. It's just an ACL where the logic is going to remain the same as other ACLs we've used, and the syntax is going to be the same. But I mentioned that there was one rule change, and here's the rule change, and it is specific to IPSec. I know that was not easy to say. The deal is that when outgoing traffic is going to be matched against a crypto ACL, if the traffic is permitted by that ACL, then IPSec will protect it. If it is denied by that ACL, and remember this is the crypto ACL I'm talking about, if it's denied by that ACL, the traffic is sent out normally. So you have to kind of switch off the thing about seeing deny and saying, oh, okay, that traffic's not going out. Well, if traffic is denied by a crypto access list outbound, then it's simply not going to be protected by IPSec. We'll talk about that again here shortly, and I'll also tell you what goes on with inbound traffic. Now again, when we're done, once the data exchange is finished, there's no reason to leave the tunnel up, and it would be unnecessary overhead anyway. Now we can configure that tunnel termination to occur after a certain number of bytes have passed through the tunnel, or after the tunnel's been up for a defined period of time. So of course there's always the chance that the tunnel is scheduled to be torn down and there's still data going through that tunnel. So what happens then? Do we want to tear the tunnel down and that data is just trapped in there? No, it's not a problem because a new security association can actually be agreed upon while the current one is still in place. Now let's go back to phase 1, and I've got here on the whiteboard for you actually a clip from a command line, and we will see this in Cisco Configuration Professional. We'll see it on the command line as well, but I want to show you these values now because this is what we're going to be working with, our crypto ISAKEMP policy with IKE Phase 1. Because when IKE Phase 1 negotiation begins, the initiator sends its policies to the other endpoint. And note that I did say policies because we can have more than one. It's very likely that we will have more than one. And that receiving endpoint is then going to attempt to find a match for those policies among its own policies. And you can see the values that we're dealing with. They're certainly very familiar to us now. We've got hash set to MD5, lifetime 42,400, but we better know if that's seconds or minutes or hours. Sounds like seconds to me. Group 5, that's the Diffie-Hellman group. Authentication, pre-share, and encryption 3 DES. Now, that number really comes into play. That does matter. That's not just for our convenience, because that search begins with the lowest numbered policy. When the inbound policies come in, the receiving router is going to start looking at 100, and then whatever you've got the next one numbered at, 200, 300, etc. Now, if that lowered number policy does not match, then the receiver will check the next lowest numbered policy. Now, I'll bring up an illustration here in a moment, but let's talk about it first. And if router 2 is getting policies from router 1, Router 2 will then start the check with policy 100. And actually, let me go ahead and filter through these real quick. And let me multiply that size. Okay. Now, we've got router 1 sending a policy to router 2. MD5, Diffie-Hellman group 1, pre-shared keys, 3 DES, and a lifetime of 86,400. Well, router 2 would simply start going through its policies, lowest number first. Well, if policy 100 is calling for SHA, and over here we use an MD5 in the inbound policy, that's not going to be a match. Then policy 200 is set for DES, which we know is just really weak. We wouldn't want to use that anyway. But we've got 3 DES coming in on a policy, so that would not be a match. And then finally, policy 300 could be our match. And again, on the board, I mentioned that the policy on R2 requires SHA, and R1's incoming policy names MD5, so that's not a match. The board goes back. Router 2 would then look at policy 200. That wouldn't be a match. Policy 300, we're assuming, meets all the requirements and the negotiation is a success. Now, we're certainly used to, at this point in our studies, especially with OSPF and EIGRP, if you've got your CCNP already, you can throw BGP in the mix there, about what values have to match. Some values have to match, some don't. The OSPF process number, remember that? You have to just keep telling yourself that doesn't have to match. Well, what exactly does have to match for a negotiation like this to work? They don't all have to be exact. We need 4 perfect matches and the 5th is conditional. And boy, this is fertile ground for an exam question. Must match exactly. Hash, encryption, authentication, and the Diffie-Hellman group number, exactly as you'd expect. The lifetime, though, does not have to match exactly. The remote peer policy must have a lifetime equal to or less than the initiator. And if it's less, the lower value will be used. So there's one particular value out of those 5 that doesn't have to match, and that is lifetime. Now again, we're going to see this live, but just mentioning here, we can verify that this is all working with show crypto ISAKEMP SA. But that SA actually doesn't exist until the entire IPSec config is in place and interesting traffic has triggered the process. That can actually be one major pain is, just testing your VPN, because you've got to do it with interesting traffic, and you got to build the entire thing before you can really test it. CCP has a built-in tunnel test that we'll see as well. Now let's talk about these transform sets and what the heck that is. Now the IPSec transform set is a group of individual parameters that enforce a security policy. The endpoints must agree exactly on the encryptions and the algorithms to create the IPSec SA. There is no gray area here. If there's an exact match, then the entire process is going to continue. If not, the process is terminated and the session will be torn down. Now, just as with the ISAKEMP policies, multiple transform sets can be configured and probably will be and sent to a remote peer, and the remote peer is going to go through the same process of comparing the incoming policies to its own. They're all going to have numbers, and you start with the lowest number, and when a match is found, then your IPSec SA is built. Now, the default lifetime of an IPSec SA is 1 hour, and we can change this with a rather long-winded command, Crypto IPSec Security Association lifetime in seconds. Those of you who have taken courses from me know exactly what I'm about to tell you, but listen anyway. I don't know if it's the thing about some people or some genders or however you want to put it, don't like to ask directions, that kind of thing. Some people just think using iOS help is, I don't know, I don't want to say beneath them, but it's almost like, well, that's just for people that, haven't memorized the entire iOS and don't know every value. Well, I'm one of those people, and I'm pretty good at this, okay? I think we can agree I'm pretty good at what I do, and I can find my way around a router, and I use iOS help all the time. It's a great way to find out other options for your commands in a lab environment as well. But when it comes to anything that is numeric, I don't care if it's a data unit, I don't care if it's a time unit, I don't care if it's a date, whatever, use iOS help and make sure you're getting it right, because there's nothing worse then, and I've seen this on job interviews more than once that I used to give, where you tell somebody to set something for 5 minutes and they don't use iOS help to see that the command takes seconds. So they would put 5. Well, there's a big difference between 5 seconds and 5 minutes in our business. And it helps you on the exam, and it really helps you out in the field. Do not be afraid to ask directions, so to speak, and to use iOS help. Now let's talk about those crypto access lists here for a minute. I mentioned that interesting traffic triggers the IPSec process. And if you have been around since the days of ISDN, which are getting further and further away, ISDN was basically when one router would place a phone call to another. And that's really not around anymore. It's not going to show up on any of your exams. But you could see immediately one issue is that we didn't want a router placing a long distance call to another router and then just leaving the line up forever just in case any data wanted to go across, because that was going to get really expensive. So we had something called interesting traffic. And when you had interesting traffic, that is what would make one router dial the other one and place the phone call. And of course, you had all kinds of termination values, time, data, that kind of thing. Now, why am I mentioning that? Because interesting traffic here does the exact same thing. It triggers IPSec. Crypto ACLs are used to define the traffic that we're going to protect with IPSec. Now, most of the crypto ACLs you write, to be blunt, they're going to be written for outbound traffic, but they can be written for incoming traffic as well, and I would bet every single dollar and cup of coffee I'm going to have in the next couple of days, I would bet anything that this is going to come up on your test somehow. Because the operation of crypto ACLs is affected by the direction of traffic. Now, we talked a little bit about this earlier, and with the outbound crypto ACL. And we've got to get used to the fact that if the traffic is identified by the ACL, if it is permitted, then it is going to be secured via IPSec. Traffic that is not identified by the ACL or is denied, it's still transmitted. We still want it to go out, but it's going to go out unprotected. Now for that inbound crypto ACL. You think, well, why would we even have an inbound crypto ACL? Because the traffic's already protected or it's not protected, right? I mean, if it's coming into us, there's nothing we can do about whether it's encrypted or not. That's correct. The inbound crypto ACL is used to identify traffic that should be coming in protected by IPSec. And if traffic is supposed to come in protected by IPSec according to the inbound crypto ACL, and it's not, that traffic is discarded, because that is suspicious behavior. If we've said, okay, traffic coming in from 172.12.123.0/24 is supposed to be protected by IPSec, and then a minute later or a week later or a month later, we get plain traffic, unprotected traffic coming in, that's a pretty big red flag that maybe we're being spoofed. Maybe it's really not coming from that network. So inbound crypto ACLs definitely have their use. And we're going to have another, actually, I'll mention this now before we head to the next video. Very important tip here, so take a deep breath. This is not any kind of filler coming up at the end of this video. Because another little detail to watch with crypto ACLs, and I say this about passwords all the time, watch your cutting and pasting. Actually, don't watch it, and don't do it. Because the crypto ACLs on the endpoints, it's really easy to think, oh, well, they should be the exact same thing. No, that's wrong. If you have an outbound ACL on router A and an inbound crypto ACL on router B, they should not be an exact match. They should be a mirror image of each other. And what's really cool about Cisco Configuration Professional is that when we're creating VPNs with that in this part of the course, it actually has a generate mirror button. And it says not to cut and paste it. I'm not exactly sure why, because I don't know why we'd be generating the mirror anyway. But the thing is, don't fall into the trap of, well, it should be an exact match. Because you're looking at two different vantage points. You're looking at one end of the WAN, and one end of the VPN, and another end of the VPN. They need to be a mirror image. I know you're getting tired of hearing me say that already, but it is the most common error with VPNs. with IPSec really, is just saying, oh, well, this crypto ACL from router A, we'll paste it on router B. It's not going to work. I will give you an illustrated view of that on the very next video. We're heading for the 15-minute mark. And then we're going to talk a little bit more about IPSec, and then we're going to do a ton of it. So I will see you on the next video.